Okay, so in this video, I'm going to explain the conservation of angular momentum. And again, I check your book, guys, and the book is, of course, does not really go into any depths of concept understanding. And I know some of you maybe just want to read this part of the chapter, and then you're going to be satisfied with the information given there. However, some of you are maybe want to get a little more explained in terms of mathematics. And so in this video, what I'll do is I'm going to go a little bit deeper into the concept here, actually explaining you why the, and I'm going to be focused on this spinning skater on page 61 of my textbook. And this is again part 3.10, angular momentum. So why the skater spinning with a different velocity when the skater, let's say, has both hands out, spinning, and leg out, versus when the skater is actually spinning, bringing the leg and the hands to the body. Okay, so I will explain the reason why I guess there would be a difference in the what's called difference in angular velocities. But before I can explain you guys this concept, I have to go into certain terms which you never learn, such as torque, such as angular velocity, angular acceleration. So I'm going to make it, try to make it as simple as possible. But ultimately, I want to explain you guys how the conservation of angular momentum will cause, by shifting the center of the mass of the skater, will cause the velocity to change also. Okay, so let's start. Let's say I have this plane, and again, there has to be, of course, a nice symmetrical circle. So just forgive me, guys, for my poor drawing. So this is let's say it's me, and I'm holding a string in here, and I have a plane here. Let's say I have this plane here that is buzzing around me, and so there is a force, net force, that this plane has, F sub t, and also, of course, the acceleration, S sub t, and this is tangential force and acceleration. And so why is it important? It is important because eventually I'll have to explain you guys the moment of inertia, which will be part of the formula angular momentum. So let's just be patient and let's get to the point where I need to get to. So now, so I got this force, net tangential force, which is produced by, this is resulted by, produced by plane's engine. Let me just erase the A for some reason I put here. Engine. Okay, so the plane, well, of course there's, if you're gonna tell me, of course there's another force, centripetal force in here, but that's not what we're talking about here. We're talking about now this net force that is moving the plane. I'm holding it, otherwise if I don't hold it, just goes straight. And so this force, again, net force is produced by plane's engine. The plane is actually making, the engine of the plane is making this plane to go around, and the reason it goes around, again, because I'm holding it by the string. So now, there's also the radius here, R, but this is also a lever, and remember, guys, we talked about the lever in mechanical advantage part of the chapter. So this is the lever. And also the plane moves around here. Let's say it's in here right now. It's moving around, this plane. Let's say it's in here. And there's constantly this angular rotation change, theta. So this is angle of rotation. This is angular rotation, and of course the plane is here. It will be bigger and bigger. So, and also the units here, rads. And again, I'm not going here into depth explaining you guys all the concepts here. It goes a little bit beyond the scope of this this textbook and of this course. So just bear with me. And so this plane is going around, it's changing this angle of rotation. The only thing that stays constant here is a lever here. And so according to Newton's second law, Ft sub t is equal to m is equal to mass of the plane times a sub t. Okay. So now, why is it important here, the Newton's second law? Because you do have a net force here, and this is the F sub t. Now, so now the torque here, the torque is produced, and let me just put the torque in again. I'm going to explain what torque in a moment because I know you guys never learn it, but it's important to understand angular momentum here. If you want to understand, we have to use the torque in here, and so the torque is equal to F sub t. Let me just correct this. The F sub t times the R. And again, the R is right here. This is my lever here. The F sub t, this is the force, the net force of the airplane produced by its engine. All right, so what is the torque though? So by definition, torque is equal to the magnitude of the force times the lever arm. And you got both in here. See, you got this F sub t right here. This is it. And you got the lever arm, which is right here. Okay, so you got torque here going on. Okay, so the mathematical expression for torque will be nothing else as F times L, where F is the Ft in this case, and L is the length of the lever arm. And so as a result, now we can say that now the torque is equal to m a sub t times the L. But the L here is R, of course. So let me just correct that. So we're trying to explain now everything in terms of what we have in front of us. Times R. Okay. So now what's important here is that tangential acceleration here is equal to R times alpha. And what is the alpha here? And again, some new term that you didn't learn before, but again, I have to, guys, explain you this. This is the change. This is the acceleration, angular acceleration here. This is angular acceleration. And angular acceleration, let me just put it here, define angular acceleration, because that will be important later on, is nothing else as change in angular velocity over the time elapsed. And the angular velocity here, this is angular velocity, and this is elapsed time, or change in time. And then the angular velocity is equal, of course, remember guys, the regular velocity is the change in the displacement, right, over the change in time. But here it will be a change in theta over change in time. And again, we know what theta is. It's right here. So this is this change in here. Okay. And just change in time, you just have to time how long it takes to change that the theta. Okay. So again, all of these terms, guys, will be important in a moment once we're getting back to the scale. So now I got my acceleration here defined in terms of my R, and the alpha, which is R is nothing else as this R here, arm of the lever, the length of it. This is my angular acceleration here, alpha. And so I'm getting to the point where now I can substitute now, instead of my A sub t, I can take now this and substitute right here in my torque expression. Let me just move it here. And so my torque now is equal to mr squared, okay, times alpha. All right. So this term now is very important now, very important in angular momentum. This is I, and I is called moment of inertia. Moment of inertia. Okay. So what I'm going to do now, I'm going to write now this formula here for I is equal to mr squared. Okay, very good. So this is the moment of inertia now. Now, so what's important here to understand is that this is constant. This is proportionality constant here. This is constant. If this is constant here, then the torque net here is directly proportional here, or directly related here to the angular acceleration. All right. So in the moment, it will be important, guys. That's why I'm getting there. Now, let's go now to the, let me just make some space here available. Let me get now to the angular momentum. So the regular linear momentum we know is equal to P is equal to M times V. And the angular momentum is equal to, according to the formula now, I times W. But again, guys, I explained you what the I is right here. All right. So I explained you what moment of inertia is. And I did explain you this W. That's not W, actually. My apology. That's omega. That's omega. And so this omega here, I just explained you here. It is nothing else. It's just the angular velocity. It's how fast this object is going around the circle here. Okay. So that's my angular momentum here. Okay. It's very important. This is linear momentum. This is angular momentum here. Okay. Now, but always bear in mind that this is m times r squared, which r is right here. This is the arm of the lever here. Okay. Now, since the total linear momentum of a system is conserved, we talked about it, guys, in the previous video. So in other words, P final is equal to P initial. So is the angular momentum. So L final is equal to L initial. Now, let's now get to the skater. So the skater, let's say this is my skater. I'm not going to draw a skater. I'm a real lousy drawer here. And so I'm going to juxtapose these two now. Just one skater, but different conditions for this one skater. So this is my axis of rotation. Axis of rotation here and here, of course. Axis of rotation. So in one case, the skater has the leg out and the hands out, rotating around this axis of rotation. And so in this now position, the skater's got her hands together and her legs together, not sticking out. You see how this one sticking out? Okay. So what's the difference between these two? And what's going to happen to, I guess, the angular velocity of these two? And the answer is pretty straightforward here. Because this skater here has more R or lever here, more R, so it's more extending. So in other words, this center of the mass here is farther away from the axis of rotation here. So what's going to happen here, let me just put here versus here, the R here for this skater, for this position of the skater will be smaller, R smaller here than R in here. And as a result, once you got the R smaller, this becomes smaller, let's say here somewhere. So what happens to your moment of inertia here? Because moment of inertia is directly related to the R square, it's gonna get smaller. Okay, so this R smaller, now this will be smaller also. But remember guys, this angular momentum is conserved. So in other words, the products of this times this must be always a constant here. So if these get smaller, then in order to compensate for this smaller, this now has to get bigger, must to get larger. And as a result now, in this particular situation, now the skater will be rotating much faster because its angular velocity will increase. And that's how you explain now this figure 3.29 on page 61 in terms of conservation of angular momentum. So I'll see you guys in the next video for the next topic.